we'll try to record this as well. Pointing out of the page, when the cross-sectional area of the loop is reduced. So we're going to take a cross-sectional area. We're going to go from some initial cross-section of 0.5 meters squared to a final cross-sectional area of 0.35 meters squared. And we're going to take a change in time of 0.3 seconds to do this. We want to know what is the average EMF that's induced inside of this coil when we do that. Okay, so to find the average EMF, EMF that's induced is equal to a negative change in flux divided by a change in time. So we're changing the flux that's going through this over some change in time. So the change in flux, we have to know what the equation for flux is. What is the equation for flux? B times A. Flux is badass. Did you give me a womp womp? Okay. Change in flux is change in B times change in A. Yep. So whichever one of those is changing is going to provide the change in flux. You can change your magnetic field, you can change your area, you can change both of them. In this particular question, what is changing? Is the magnetic field changing? Area is the only thing changing. So we have the magnetic field and the change in the area. What's the change in area? A final minus A initial. Okay. So our change in flux, we can calculate that, is B of 1.5 times the change in the area, 0.35 minus 0.5. Okay. If I want the EMF, then I take that negative change in flux and I divide it by the change in time. So I have negative 1.5 times 0.35 minus 0.5, all divided by the change in time of 0.3. And there I get my change in EMF. My induced EMF is 0.75. If you reverse the direction of your areas, technically that's not quite right. So your change in an area is always the final minus the initial. And if you plugged everything in, you'd get a negative answer. If I do 0.5 minus 0.35, I end up with a negative. That wasn't one of the answer options, so you would have been fine.
Yeah, I didn't have negative 1.5, though. I just did I did 1.5. Like I
So,
kept everything positive. Yeah.
Got to remember that negative right there.
Yeah, that's what
And where does that negative come from? Lenz's law. Is that Dr. Lenz here?
Yep.
No. Different Lenz. That Lenz was a dude long, long time ago. Yeah. Any questions on number 5? Quiz question number 5. Yes? Chapter 31. Oh. Let's rename this. Let's do problem.
Didn't you just pause yourself?
Let's do problem number 15. No, it's recording. It's counting. I don't know why it stopped recording. I was recording and it just stopped. Whatever. It's technology. This is all just for your benefit anyways.
That's why we want it recorded.
Yeah, and if it doesn't record, then you got it in class. So, yeah. How often do your other professors record everything that they do in class so that you can watch it later? Do any of them? No. No. They're horrible people. Physicists are great. Let's do problem number 15. I like problem 15. So we have large superconducting magnets that are used in hospitals to produce pictures of the interior of the body by magnetic resonance imaging, MRIs. How many of you have had MRIs? Yeah? If you have the files from your MRIs, you can bring them in and we can 3D print you. We can 3D print your brains or your skulls or whatever. Okay, so for this purpose, and I love this problem. I love the way they write this problem. For this purpose, the patient is shoved within the coils of the magnet where the magnetic field is 1.5 Tesla. Does that seem like a good idea? Yes. Shoving your patient into this giant magnet. Those things are terrifying and you're shoving your patient in. You're just a bad technician. We're shoving them into this magnet that has a magnetic field of 1.5 Tesla. That magnetic field is stronger than the magnetic field of the Earth. So these are very strong magnets. Suppose that the patient is shoved into the magnetic field in a time delta t equal to 10 seconds. Estimate the EMF that's induced around the patient's trunk. The patient's trunk, whatever that means, is a circumference of 0.9 meters. Should the patient be shoved into the magnetic field more slowly? What the heck?
Yes.
What the heck are they asking? I have no idea what they're asking. How could I figure out what they're asking? What is this whole chapter about?
Magnetic flux.
This whole chapter is about EMF and induction, so we need to figure out what EMF we're going to induce inside of this patient. EMF is equal to negative d phi dt. EMF physically is a voltage. We need to figure out what kind of voltage we're inducing inside of this patient. So you are putting electricity into them just by shoving them into this magnet. You are changing the magnetic field that they're exposed to. By changing that, you induce current. You're going to make current flow through them. Could you stop their heart?
Yes.
Let's see. Yay! Let's kill some patients. Negative d phi dt. So if we were given an equation for this flux, we could plug in an equation for this. We're not given an equation. We're just given this this b and this this trunk size and this change in time. So let's write some things out. D phi, what's that?
CDA.
B times dA. The magnetic field isn't changing, right? The area that I'm shoving this patient into is changing. I go from having zero amount of their body inside of this to all their body. So I'm going to have some area. And then we have a change in time. So I'm given a B. I know what that is. So I can plug in negative 1.5. I have some change in area. I don't know what that is. Divided by a change in time, that's 10 seconds. So I need to find out what's the change in area. That's the change in the cross-section area of this patient's trunk. What does that mean? What is a patient's trunk? An elephant?
Cylinder.
Cylinder. You are assuming that this person is a cylinder. Here's my person. They're very skinny. I'm shoving them into these magnets. So there's my patient, and I shove them in. Right? In how many seconds? 10 seconds? Is that really shoving somebody in?
No.
10 seconds. Let's say this is my MRI magnet right here. 10 seconds to get in there?
Seriously,
Right, I am not shoving that patient in. If I'm shoving the patient in, yeah, that's really shoving. Maybe we'll calculate how fast we can shove them into the magnets. That'll be fun. So, the trunk, the area that's going in, is the area of this circle. It's the cross-section if I were to cut a slice of this. So what is the cross-sectional area of this? Can I get it? What did they give us? They gave us our trunk as their circumference of 0.9 meters. How do I use that to get the area?
I'm going to just say it goes from 0 to 0. You're going from not having.
Nothing inside of the box. Nothing inside to
You have to find the radius. and then
have to
plug-
find the radius
Yeah, and then plug that into
to the area. What's the area? Somebody said it. Pi r squared. So I have to find the radius. How do I find the radius from circumference?
C equals
2 pi r equals 0.9. R equals 0.9 divided by 2 pi. Somebody take out a calculator and tell me what that is. What you got?
0.143.
0.14?
Yeah.
Okay. So I can plug that in to find my area. Pi times 0.14 meters squared. What do I got? 0.064?
Yeah.
What are the units?
Meters squared.
Meters squared. Perfect. Okay. So I can plug that number in, and let's find out if we're going to kill our patient. Yeah? So the EMF that's induced is negative 1.5 times 0.064, all divided by 10 seconds. What is it?
Negative 0.009.
Negative 0.009.
7.
What are the units? Volts. Is that a dangerous voltage? Are we going to kill our patient? No. Can we shove them in faster?
How do we know if it's a dangerous voltage?
What is a dangerous voltage? Can I touch two sides of a battery? We talked about this in previous How many volts is the double A? 1 volt. How about a 9-volt battery? Can I touch a 9-volt battery? Yeah. What else can I do to a 9-volt battery? You can lick it, and it shocks you a little bit. Does it kill you? No. What would kill you? That. If I lick that. That. How much voltage?
120.
120. So about 100 volts will kill you. So we can calculate actually how fast we can shove somebody into this magnet. How fast we could have to shove them in to kill them. Bless whoever. Feel like sometimes when you guys sneeze, I need holy water. Some of your sneezes sound like demons. Not that one. Other ones do. It's terrifying. So what if I told you that 100 volts is the maximum voltage that you can induce in your patient? Otherwise, you're going to kill them and you're going to get sued. So I have to know how long I can take. What's the time that I can use? What's my safe time range? How can I figure that out? So if I have an EMF of 100, so I can plug in 100 equals, my magnetic field is still going to be negative 1.5. My area, still 0.064. And I can divide by the change in time, whatever the change in time would be. So what change in time would I need? So I can move my change in time over to the other side, and I get change in time has got to be 1.5 times 0.064, all divided by 100. That's my change in time is what? .00096 seconds. How fast is that? Right? Shove them in. That's like. That's ridiculous. Would you want to shove your patient into the MRI that fast?
I don't think the machine even moves that fast.
No, you don't want to shove. What's going to happen? Well, you're shoving them in and like they're wearing a hospital gown, right? Those things are pretty slick. They're just going to keep flying. They're just going to keep going. And then they'll become a projectile. And you can calculate where they'll land using physics. This is a comprehensive problem.
It stops. The machine cuts off. You can't just keep going.
You can't?
No.
They're not completely open? You can't go flying? So then it becomes a momentum question, and your head bangs into the back, and then you can calculate how much force they'll get to crack their skull open. So this is why you want to know some physics if you're doing some MRIs.
I just trust
Don't kill your patients. Any questions on that one? That's one of my favorites. I love that question. I just like that they're shoving patients into MRIs.